Let's go to another interesting concept called bond enthalpy. If you remember in the chapter chemical bonding last year, we did come across this concept on bond enthalpy. It's basically the energy required to break a particular bond and not to form a particular bond. Remember, this energy is is due to breaking of a particular bond. Now, so the enthalpy change necessary to break a particular covalent bond in 1 mole of gaseous molecules to produce gaseous atoms and or radicals is called bond enthalpy. For example, hydrogen molecule when it is broken into its atoms, that is H plus H, this is the bond enthalpy, that is 436.4 kilojoules. Similarly with chlorine gas, when it is broken down, when this bond is broken, what is its bond energy? 242.7 kilojoules. So that much of energy is required for it to break this bond. Okay, similarly with HCl. Now when it is broken, when the bond is broken between H and Cl, okay, this is how it is denoted. This is how it is denoted when we talk about breaking of bond. So how much energy is required for HCl to break? 431.9 kilojoules. Now there is a very interesting and important concept called Hess's law of constant heat summation. Now it's a five-star question, very important from examination point of view. What does this law say? The enthalpy change for a reaction is the same. I repeat, the enthalpy change for a reaction is the same whether the reaction takes place in one or a series of steps. Okay? It's just like saying when you leave your home from point A and reach Don Bosco, which is point B. Okay? Let's call it Don Bosco D. Okay? So from A, the destination is point D. Okay? So from A to D, you require, suppose, 50 kilojoules of energy. Now 50 kilojoules of energy from A to D. But what you do is, meanwhile, there are some stations in between wherein you go from A to B, which requires 20 kilojoules energy, from B to C, which requires another 20 kilojoules, from C to D requires 10. So when you add A to B, B to C, C to D, it comes out to 50 kilojoules. And when you take a route from A to D straight away, the energy taken is 50 kilojoules. So whether you take that one direct uh, route to come to Don Bosco or you go to different stations, the energy required would be same. That's what this law says. So I'll repeat that statement. The enthalpy change for a reaction is the same whether the reaction takes place in one or a series of steps. Or the other statement is the enthalpy change for a chemical reaction is the same regardless of the path by which the reaction occurs. So the path really doesn't matter. As long as the destination is achieved, the enthalpy change remains the same. Okay, you can see over here, I've given an example with methylene chloride. There are two paths for it to form methylene chloride using methane and chlorine gas. So this is one direct path. So what is the enthalpy? Minus 202.3 kilojoules. But if I take another path which goes through different steps, so there are two steps to it. It forms methyl chloride in this case, and then eventually methyl chloride gives methylene chloride. So look at this, minus 98.3 for this first step. Okay, and for the second step it is minus 104, but when you add, it becomes same as this one, that is minus 202.3 kilojoules, and this one is same. So you understood. So irrespective of the path that is taken, the enthalpy change remains same. Let's come to another topic, that is entropy and spontaneity. Okay, entropy and enthalpy, my dear students, both are very important terminologies in chemical thermodynamics. We've understood what enthalpy is in all the previous explanations. Now, entropy is a measure of molecular disorder or randomness in a system. So, we are looking at another important term related to chemical thermodynamics, that is entropy. No, so entropy, as I've already told you, is a measure of molecular disorder or randomness in a system. To give you a very simple example, when you keep a cube of ice on the table, so spontaneously what happens is the solid ice starts melting. So you don't need a non-spontaneous reaction, right? So it's just a spontaneous process wherein Ice, which is solid in nature, starts melting and becomes liquid. So that's spontaneity of a process. Okay. So there is a disorder or randomness that you get to see, and the measure of it is entropy. Okay. So the total entropy change in a process is given as delta S total. Remember, the symbol of entropy is S, but while calculating, we always consider the total entropy change, that is delta S. Now, what is delta S total? It is the sum of entropy change taking place in the system and the entropy change taking place in the surrounding. And usually, the entropy change in the system is denoted as delta S. So, whenever you come across delta S, it means they're talking about delta S of system. Okay, so now what would it mean if delta S is positive or negative or equal to 0? If delta S, that is total, is greater than 0, it means the process is spontaneous. If it is greater than 0. If it is less than 0, it means the process is non-spontaneous. When I say process, means I'm talking about reaction. Okay. So if the delta S total is equal to 0, that means the process is at equilibrium. Okay. So if it is greater than 0, spontaneous, less than 0, non-spontaneous, equal to 0, the process is at equilibrium. So entropy and spontaneity, they go hand in hand. No, I give you an example of ice cube. So there are many other examples wherein it doesn't happen spontaneously. For example, if I have to convert liquid into ice, will it happen naturally? No. I'll have to keep it in a freezer. So it's a non-spontaneous process. Unless I change the temperature, liquid will never ever become ice. Okay. So that's how entropy and spontaneity work. Coming to another very, very important term in chemical thermodynamics, that is Gibbs energy. Now, Gibbs energy is denoted by letter G, which gives a relationship between those two important thermodynamic properties, that is enthalpy and entropy, that is H and S. So, how are they related? So, Gibbs energy is nothing but the difference between enthalpy and the product of temperature and entropy. Okay, that is T and S. So, the change in Gibbs energy at constant temperature and pressure is given by this equation. Delta G is equal to delta H minus T delta S. So temperature is kept constant. Okay. So delta G is equal to delta H minus T delta S. Now just like how we saw for entropy, Gibbs energy change, that is delta G, when it is greater than 0, it is non-spontaneous. Remember, for delta S, when it was greater than 0, it was spontaneous. But delta G, when it is greater than 0, it is non-spontaneous. Delta G, when it is less than 0, it is spontaneous, whereas delta S, when it is less than 0, it is non-spontaneous. What is common between delta S and delta G is when it is equal to 0, the process is at equilibrium. So when delta S is equal to 0, delta G is equal to 0, the process is always at equilibrium. So that is one common thing that you will see in Gibbs energy change and entropy change. So when the process is at equilibrium, we said delta G is equal to 0. So what will happen to that equation? This equation delta G is equal to delta H minus T delta S. Clearly, we can substitute delta G is equal to 0. So what we'll get is T is equal to delta H upon delta S. Why? Because if this becomes 0, so I can rearrange this equation to delta H is equal to T delta S. Therefore, T is equal to delta H upon delta S, since delta G is equal to 0 at equilibrium. So we get an equation like this at equilibrium. Now, if I have to know the relationship between standard Gibbs energy, remember whenever there is a zero on top, okay, it means we're talking about the standard quantities. Okay, so relationship between standard Gibbs energy and equilibrium constant can be given with this equation. So delta G, which is my Gibbs energy. Okay, so if I have to give relationship between standard Gibbs energy and equilibrium constant, we have a fresh equation. Delta G is equal to delta G0 plus RT ln Q. Remember, ln is what? Natural log. Delta G is what? Free energy. Delta G0 is standard Gibbs energy. Okay, so when I say standard Gibbs energy, that means at a particular constant temperature and pressure. Okay. Now, what is Q? Q is the reaction quotient, which is similar to equilibrium constant. Remember, we did the chapter called chemical equilibrium. That time we did come across equilibrium constant. So the letter Q is equivalent to equilibrium constant. Okay. So, for example, if I look at a reaction like this, AA plus BB arrow CC plus DD. So in that case, what happens is delta G is equal to delta G0 plus RT ln QC. Okay, so since I'm talking about the products, so I look at the products which is equal to delta G0 plus RT. Now what is QC? QC is nothing but, something. If you look at this part of this equation, you'll be able to relate with that uh, equation which is there in the chapter chemical equilibrium, with equilibrium constant, law of mass action. So it will be Cc multiplied by Dd upon Aa into Bb. Okay, so Ln stands for natural log. Or in terms of pressure, okay, so in terms of pressure, now this is in terms of concentration. Now in terms of pressure, what will happen is this will become Pcc multiplied by Pdd upon Paa into Pbb. So here reaction quotient, you can clearly see it is relatable to what we know about equilibrium constant, which is nothing but the ratio of products of the concentrations, okay, and the concentration of the reactants in the denominator. Okay, so that's what the relationship between standard Gibbs energy and equilibrium constant is. Moving on, so when the reaction reaches equilibrium, that is delta G, standard Gibbs energy becomes zero, then QC and QP become KC and KP respectively. Okay, so that reaction quotient of QC and QP, what do they become? They become KC and KP. So KC is what? Equilibrium constant with respect to concentration, and Kp is equilibrium constant with respect to pressure. Okay, so thus this equation, this equation here, delta G is equal to delta G0 plus RT ln QC, can be written like this: 0 is equal to delta G0 plus RT ln Kc, because QC becomes Kc, and 0 is equal to delta G0 plus RT ln Kp. Okay, so therefore I can, so here by mistake there was a 0 here, so delta G is equal to 0. Yeah, so when I substitute the values, so this is what I get. So delta G 0 is equal to minus RT ln Kc, and delta G 0 is equal to minus RT ln Kp. Okay, so now delta G0, when I convert that natural log to log to the base 10, remember I told you need to multiply with a factor like 2.303. So delta G0 is equal to minus 2.303 RT log to the base 10 Kc, and delta G0 is equal to minus 2.303 RT log to the base 10 Kp. Okay, so this is about relationship between Gibbs function equilibrium constant, and also an equation wherein delta G, that is Gibbs energy, is equal to 0. And finally, my dear students, we look at third law of thermodynamics. We looked at first law of thermodynamics, we looked at second law of thermodynamics, and now the third law of thermodynamics, which says, which is the final part of this chapter, it states the entropy of a perfectly ordered crystalline substance is zero at absolute zero of temperature. Now, what does this mean? Remember, what is entropy? Entropy is disorderliness, randomness of a system. Okay, so that's what entropy is. But if the substance is completely perfect, okay, so there is no disorder in it, there's no changes happening, so that's obviously the entropy will be zero. Okay, it won't be negative, it won't be positive, but it will be zero at absolute zero of temperature. That's what third law of thermodynamics states. So, my dear students, as far as theory is concerned, we are done with this chapter. Okay, please go through these videos carefully, try and understand. We will be doing numericals in the class. Okay, so yeah, thank you and see you in the class. God bless.